This video will look at the chi-square test for independence. The test for independence looks to determine if there is an association between two variables of bivariate data. So let's take a look at this problem. It's called Deceptive News. It was from the article When News Reporters Deceive the Production of Stereotypes. The researchers investigated the relationship between authenticity and tone for the news stories. Tone was measured by using a method of coding sentences and was categorized as positive, neutral, or negative. So let's take a look. We have 311 news stories that were either determined as authentic or deceptive. And then the tone was measured for each of these news stories. The tone was either negative, neutral, or positive. So the question is, at the 5% significance level, do the data provide sufficient evidence to conclude that an association exists between authenticity and tone? So let's start with our two hypotheses. When we're doing a test for independence, you can talk about independence or you can talk about association. For this particular problem, remember, it's always easy to come up with the alternative hypothesis first by reading this question. An association exists between authenticity and tone. So very simply, we can, for the null hypothesis, say, for the, alternative hypothesis, state that tone and authenticity are associated. The null hypothesis for test for independence is always going to be that there is no association. So tone and authenticity are not associated. So as we did in the last problem, in the last video, when we looked at observed and expected values for any chi-square problem, the formula is going to be exactly the same. Chi-square equals the summation observed minus expected squared divided by expected. For this particular problem, we are looking at a 5% significance level. Our sample size is 311. We know our observed values. That's the 59, the 111, the 49, the 61, the 20, the 11, everything in this bold box. We're going to use our marginal values and our total to come up with the expected values. I'm going to move this down a little bit. As you recall from last time, you're going to calculate the expected values by the row times the column divided by n. So if we want to look at the box that's negative and authentic, the row for that box is 170. The column for that box is 128 divided by 311, and then that is going to equal 69.968 is what I got. So that's our expected value for this first box. Our observed value is 59. The expected value is 69.968. You will need to do that for the 6 numbers within this bold box. So if I scroll down, you see that this is done for you. We have the expected number on top and the observed value underneath for each. So what you can always pause, try to find the rest on your own. and make sure you're getting the correct numbers. Now, we have 6 expected values and 6 observed values, so our summation is going to have 6 subtotals. For each of these subtotals, going with the same box, the negative and authentic, we are going to have to do observed. The observed was 59 minus our expected 69.968, square that, divide by the expected 69.968, and for that answer we get 1.719. Yes, you need to do that for every box. Here are all the subtotals to get your chi-square, so you can try it and see that you get them correct. At this point, your chi-square value is going to be the sum of all 6 of those, and that sum comes to about 10.427. Now let me stop you and calm you down for 1 second. You are still, even though you're taking these tests at home, you're still only going to have so much time. I'm not always going to make you do all these calculations. I might ask you to fill in some of the expected values, so I know you know how to do that. I may give you the chi-square test statistic already completed in the problem, so please read the problem carefully and do what's being asked. You're not going to have to do all, this can get very tedious. You're not going to do all these calculations for everything. All right, so for this particular problem, now that we know our chi-square test statistic, let me just scroll up and remind ourselves. We had a significance level, an alpha of 0.05, and was 311. Okay, I want to remind you how to do both approaches. So we're going to start with the critical value approach. All right, and if we recall, you always draw, you know I like the pictures, draw the pictures. Draw a picture of your chi-square. To do the critical value approach, you would need to put the critical value of a chi-square test statistic at the 5% significance level. So we want chi-square of 0.05. But to do this, we need to know degrees of freedom. So let's stop for a minute real quick, go back to our formula sheet, and let's look up degrees of freedom for a test for independence. It's going to be the number of rows minus 1, the number of columns minus 1. Okay, so that's where it is, right underneath your test for independence chi-square formula. So we'll go back to the problem. In our original problem, we have 3 rows. So 3 minus 1 is 2, and we have 2 columns. So we have a 3 by 2 contingency table. So the degrees of freedom is 3 minus 1, 2 minus 1, which is 2 times 1. We should have 2 degrees of freedom. So we're looking at 0.05 at 2 degrees of freedom. We'll go to your chi-square table. Erase what I did last time. We're still at 2 degrees of freedom. And I want 0.05, which is this value, looks to be right here, 5.991. So my critical value is 5.991. So if you recall, we do a critical value approach. We have a rejection region and a do not reject region. Think of all of these are just as a right tail test, so you only have one rejection region. And our test statistic was 10.427. Well, that clearly is out here, the test stat of 10.427, which would lead us to say we are going to reject. Now, I want to show you also the p-value approach. Because again, on a test, you don't know which approach I'm going to have you do. You can still draw the picture, but this time when you draw the picture, it's your test statistic that's going to go in this location. That was the 10.427, and this area is going to represent your p-value. So we still need to go back to our table. We still have 2 degrees of freedom. Go back to the chi-square table. Go back to 2 degrees of freedom. But this time, we are going to look for 10.427 on our chi-square table. 10.427 appears to be right between these two values, right? It's more than 9.210, but less than 10.597, which means the p-value itself is between 0.0005 and 0.01. Here's 0.01, here's 0.005. Remember though, we never write it like that. Smaller number goes first, p in the middle. P is greater than 0.005, but less than 0.01. So that's what you're going to put for your p-value. I'm going to move that up a little bit. We have p is greater than 0.005, but less than 0.01. We know that alpha equals 0.05. That was a 1, by the way. I don't know why I wrote a 5 there. Sorry about that. Alpha was 0.05, and clearly p is smaller than alpha, which also, of course, leads us to reject. Your last part, let's go back and look at the original problem. The question was, do the data provide sufficient evidence to conclude that an association exists between authenticity and tone? Of course, we would now write at the 5% significance value, the data do provide sufficient evidence that an association exists between tone and authenticity. Okay, thanks.